Hello everyone, welcome to our channel OnlyPhysics JEE Grad. So today we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter magnetism. This will be the first video on this chapter, and the topics we'll be covering are Biot Savart law and Ampere's law. So there are a total of 22 questions from these topics, and today we'll be only discussing 17 questions, right? So let us start with our first question. So in this question, there is an infinite hollow cylinder, conducting cylinder, of course, with inner radius this and outer radius is this. So we have a cylinder like this, okay, and there is this internal radius, okay. Now look, current is in this region, okay. So current is in this region, right? Because it's hollow. So current will be in this region, right? Now in question, we have to plot magnetic field versus R, right? So look, for small r by 2, so this is inner radius is small r by 2 and capital radius is the outer radius is capital R. Okay, so we have to plot magnetic field with R. So for r by 2 there is no current, so I is 0 here, right? So there will be no magnetic field, right? So if I start to plot like this, okay, so there is no magnetic field till r by capital R by 2, right? Now after that I have to make a loop like this, Amperian loop, which is of the radius small r, let's say. So let's write the magnetic field. So it will be b into 2 pi small r. It will be equals to mu naught I enclosed. I enclosed will be, let's say, sigma is the current density into area. So area will be pi small r square minus this r by 2, right? So pi small r, capital R by 2 whole square, right? So we'll get magnetic field will be mu naught sigma upon 2 pi small r, and this will be pi will take common, and this will be r square minus capital R square by 4, right? Perfect. So this will get cancelled and we're left with mu naught sigma upon 2 small r square minus capital R square by 4, and this will be till r, right? This will be till r. So actually it is not linear, so B option is incorrect, and A was already incorrect because till r by 2 magnetic field must be 0. So A is incorrect, B is also incorrect. For C and D we have to choose among these two, right? So let's put the value r by 2. So if you put r by 2, so be at r is equals to r by 2. Let's check how much it will be. This will sigma 2 capital R by 2, and this will be r square 4 minus r square by 4. So this will be 0. Look, this graph is starting from like this point. So it's saying that just after r by 2 there will be magnetic field, but our equation says no, there will not be any magnetic field. So D is correct, C is wrong. Okay, let's move on to next question. So let's move on to our next question. Perfect. So we have some lines, right? They are not infinite, of course. The length are given, and we have to find the magnetic field at O. Okay, perfect. So look, this is a wire. Let's first check from only which wires will have magnetic field. So with this wire, can we have magnetic field at O? Yes. For this, no, it will not be. There will not be magnetic field because it is passing through this part, right? Uh, the perpendicular distance is 0, right? This point lies on the direction of current itself. From this semicircular loop, yes, there will be magnetic field. With this section, no, there will not be. From this section, quarter circle, right? Yes, there will be magnetic field. With this, there will be no magnetic field. So we have to check for 1, 2, and 3, right? Let us find for B1. right? Magnetic field due to first wire. So direction will be minus k cap, right? You can use right hand thumb rule. Now the magnetic field will be, so it was mu naught I upon 4 pi r. R will be, this is L by 2, this is L by 2, so this will be L. Sin theta 1 plus sin theta 2. Sin theta 1 is 0, so sin 0 plus sin theta 2. So this is theta 2, right? So look, this is L and this is also L. And this is theta. So it will be 45. So we'll just write sin 45, right? So we get mu naught I upon 4 pi L 1 by root 2 minus k cap, right? This is P1. Let's find B2. So B2, the radius is L by 2. So we'll just get mu naught I upon 4 and the radius is L by 2 and direction will be minus k. So it will be equals to mu naught I upon 2L and this will be minus k cap, right? Right? For B3, magnetic field due to third loop. So this will be mu naught I upon 8 and the radius will be L by 4. So it will be L by 4 and direction will be again minus k cap. So we'll get mu naught I upon 2L minus k cap, right? So let's add all these because these are vector. So direction is minus k cap and we'll get B total will be mu naught I. This will be 4 root 2 pi L plus this will be mu naught I upon 2L plus 2L. So it will be simply L and the direction is minus k cap. Okay. So which option is correct? Mu naught I by L minus k cap. So these two are wrong. So C and D may be correct. And there is 4 root 2. So C option is correct, right? Okay. Let's move on to the third question. Right. So we have, this is our third question. We have a long wire on Z axis carrying a current I in negative Z direction. Perfect. So let's make axis like this. Okay. So let me rub this. Now the current is, let's say this is X, this is Y, and this will be minus Z, right? And the current is in this direction. Okay. Or let's just represent it by a dot. Okay. It is a bit confusing, I guess. So let's just write like this. So it will be cross, right? This is our current. Now in the xy we have to find. So let's take a point, journal point x comma y, and this will be r. Right? It is a perpendicular distance. There is no worries. And the magnetic field, if you use right hand thumb rule, it will be in this direction. Okay. So let's take this as theta. So this will be, so these are perpendiculars, right? So if this is theta, this is 90 minus theta, this will be theta. So this will be theta, right? So here we'll get a b cos theta and here we'll get a b sine theta, right? Perfect. So let's find the magnetic field. So it will be b sine theta I cap plus b cos theta minus j cap, right? So let's find the b. So b will be mu naught I upon the infinite, due to infinite, it will be 2 pi r, right? And sine theta will be perpendicular. So this perpendicular is y by r. Okay. Plus again b will be mu naught I upon 2 pi r and cos theta will be base. So base is x upon. So this was I cap, right? X upon r minus j hat. Okay. So r is what? It will be root x square plus y square. So we'll get answer answer will get mu naught I upon 2 pi r square. So 2 pi x square plus y square, right? And this will be y I cap minus x j cap. Okay. So mu naught I upon 2 pi x square plus y square, y I minus s. So A option is correct. Right. Let's move on to our 62 question. Right. So this is our fourth question, right? So we have a coil having n turns is wound tightly in a form of a spiral. So you know spiral, so it will be like this, right? So there are n turns in a form where inner radius is A, so this is A, and outer radius is B. Let me rub a portion a little bit like this. Okay, so this is inner radius is A and outer radius is like this B. There are total of n turns. The current I is passed, find the magnetic field at the center. So let's say this is our center. Okay, so you must have done this. We'll take at a distance r, will take a small loop, right? We'll take a small loop whose thickness is dr, right? So magnetic field due to this loop will be mu naught I by 2 pi small r, right? Now we have to find this I. So this the current it will be having. So if this thickness is dr, there will be, look, there are n turns in B minus A, right? Or we can write it in the opposite manner. This is just a unitary method, right? So we know in B minus A there are n turns. So in one there will be n upon B minus A turns, right? So for this dr thickness, there will be n upon B minus A into dr, right? And if these number of turns are there, then current will not be just I. So it will be I into n dr upon B minus A. Okay, and this is our integrating element. So the magnetic field will be very small and we have to integrate. So B will come out to be mu naught I upon 2 pi B minus A. They are constants, right? Integral dr by I. So from where we have to integrate? From A to B. So we'll simply get mu naught n I upon, so this is capital I, 2 pi B minus A. Okay, so due to loop, there will not be a pi, right? So pi will not be there. It will be just r, right? Ln B by A. Okay. So which option is correct? C option is correct, right? Perfect. Let's move on to our fifth question. So we have two questions. This is our fifth. This is our sixth, right? So for fifth question, we have a non-planar loop of conducting wire carrying a current I, right? Sorry, is placed like this. So this is folded like this. Each straight section is of length 2L. So this is 2A, this is also 2A. This is also 2A. So it looks like this is small, but this is 2A. Okay, this is 2A. Perfect. The magnetic field due to this loop at a point P is A comma 0 comma A. So it is in the XZ plane. So this is our point, right? So we have a point like this. Okay, and let me make the axis like this. Okay, and we have a plane like this. So this is our plane, and here we have to find this, let's say this is our point a comma 0 comma a. This is just x, this is z. So we have a plane like this. Okay. Now what we can do to solve these type of question, if you try to find the magnetic field due to each wire, it will be really complicated, but you can solve it. But what we can do, we can do a strategy like this. Let's say this is our plane, this is our one side. We take a strand wire like this and another wire like this. Okay, and this is our second loop, right? Look, the current is flowing in this direction like this, and in this it will be like this, right? So actually there is no current here because these wires are so close that the current is not there. And due to this, the situation will become very easy. We just have to find the magnetic field due to this, and we know it will be in x direction, right? So let's say this is our first plane, this is our second plane. So magnetic field due to 1 will be in x direction, and magnetic field due to this will be in z direction. So this is P2. Okay, right? Due to this plane, it will be in this direction, and due to this plane, it will be in this direction. So net magnetic field will be in x and z direction only. Are you getting me? Is it, isn't it interesting? Right? So let's check the options. So from the options, we can directly find I and J, I and K. So only D option is correct, right? Other options are incorrect. Okay, perfect. You can find the exact answer also. There is no big deal with this. Oh, but why make it complicated? It just wants us to find the direction, right? So it will be I plus J, right? So very easy question. Let's move on to our sixth question. So we have an ionized gas contains both positive and negative ions. Okay, if it is subjected to simultaneously to, so in x direction, let's say this is our x direction, we have electric field, and let's say this is our z direction. Okay, this is x, we have electric field. In z, we have magnetic field, right? Okay, positive ion deflect towards y. Let's check. So this will be our y, right? Perfect. So let's say we have a positive here. We have a positive here. So positive will deflect here. So it will get some velocity. As soon as it get a velocity like this due to electric field, right? Due to magnetic field, it will get force in minus y direction. So it will start to have magnetic force like this, right? And where will it deflect? It will deflect like this, right? There will be a force in this direction, of course, but the deflection will be towards minus y, right? So it will move like this. Okay, so it will move like this. So where positive will deflect towards minus y. Okay, so we'll check the options. Let's move on for the negative. So if we have negative here, now due to electric field, negative will move like in this direction. So it will get a velocity in this, right? Now, due to magnetic field, if you use right hand thumb rule or Fleming's left hand rule, whatever, the right, so it will be having a force in minus y again. So force, it will be having force in minus y again, right? Due to magnetic force. So deflection will be again like this. Okay. So both positive and negative are deflecting towards minus y, right? So which option is correct? All ions deflect towards minus y. Yes, this is correct. C option is right. Okay, let's move on to our seventh question. So we have two questions, seventh, and this is eighth. So this is a wire, infinite wire we have. PQR is bound to form like this. The magnetic field due to this current at point M is H1, and now another infinite long straight wire QS is connected at Q, so that the current is I by 2 in QR as well as QS. Perfect. The current PQs remain unchanged. The magnetic field at M is now H2. Okay, so this is quite easy. For P, this is a semicircular. So initially, let's say H1 at M will be, let's say this distance is A. Okay, and it is semi-infinite. So magnetic field will be mu naught I upon 4 pi A, right? And the direction will be outwards, out of the plane, out of the plane, right? Okay. Now, as soon as you connect a wire QS, so we have this semi-infinite wire is having current I, but this section is having current I by 2. For the QR, there will be no magnetic field at P, right? So current at this point, there the perpendicular distance is 0. So let's find H2. So H2 will be for this. It will be remain same mu naught I upon 4 pi A, but for this it will be plus. The direction will be same mu naught I by 2 upon 4 pi A. So we get mu naught I upon 4 pi A, we can take common, this will be 3 by 2. So if you divide H1 by H2, H1 by H2, you will get 2 by 3, right? So which option is correct? C is correct. Okay, again, quite easy question. Let's move on to our eighth question. So we have two long parallel wires are at a distance 2D apart. Okay, so we have a wire like this, and they are 2D apart. The equal current flowing out of the plane in both, right? Okay, the variation of magnetic field. So this is quite easy again. In the center, magnetic field due to this wire will be in the downward direction, right? So with this wire due to it will be in upward direction. Sorry. So this is, let's say this is 1, this is 2. So B1 is here, P2 is here. Right? So at center it will be 0. So the all options saying yes. As you move towards one wire, the magnetic field will shoot to infinity. Right? So as you approach, due to first wire, magnetic field will shoot to infinity. And look, the magnetic field due to first wire in this region, it is in upward direction, so it is in positive, right? So this D option is incorrect. So let's make the diagram. So here it is 0, here it is short to infinity, and for P2 it will be short to infinity in the negative direction. So it's like this. Okay, now just here, the magnetic field due to 2 will be upward direction, and it will again short to infinity. So it should be like this, and as soon as you go, it should be 0, right? And just here, just in the left of one, the magnetic field will be in downward direction, and it will again going to be at infinity. So it should be like this, right? As soon as you go infinity, the magnetic field you do wire will be will approach to 0. So which option is correct? So option B is correct, right? At infinity, they will not be 0 at exact because these are infinite. Yes, so it will be 0 because magnetic field is mu naught. Magnetic field due to infinite wire is mu naught I by 2 pi A, right? So if A shorts to infinity, B will be 0, right? So yes, it will be 0. So which option is correct? B is correct, right? Perfect. Let's move on to our next question. Ninth, ninth question will move on to. right? So we have ninth question. In this, a battery is connected to 2 points A and B on the circumference of a uniform conducting ring of radius R. Okay, so we have a ring. So we have a ring like this. One of the arc AP of the ring subtended angle theta at the center. So we'll consider this as a point A and this as a point B. And we have a battery connected like this. And it is making an angle theta at the center, right? So the value of magnetic induction at center due to current in the ring is, so we have done this. So whatever the be the current or whatever be the value, so current will automatically divide according to their resistance, and hence the magnetic field at the center will be zero for any value of theta, right? So actually D option is correct. Okay, you must have solved it. This is quite easy. Okay, let's move on to our 10th question. So here we have two concentric circular loops, one of radius capital R and other of radius 2r, lie in the xy plane. The origin as their common center. Okay, perfect. The smaller loop carries current I1 in the anti-clockwise direction. So this is I1 and this is I2 in the clockwise direction. And we have given I2 is greater than I2I1. So I2 is greater than 2I1. Okay. Now Bx represent the magnetic field. Okay, perfect. Which of the following statement is or are correct? Okay, let's start to check these options. So let's go with our first option. So we have that BXY perpendicular to the XY plane at any point in the plane. So let's first uh, analyze this situation. Okay, so we have these two loops like this, right? Current in first loop is in this direction, so I1, and current in this loop is in this direction. So look, first let's check the magnetic field at the center. So at the center, due to this, it will be in outward direction, right? And due to this, it will be in inward direction. And we'll check later which one is greater. Don't worry. So let's just check the magnetic field near this wire. So due to I1, it will be in this direction, right? Out of the plane. But here it will be in this direction, right? For I2, for I2, magnetic field will be in this direction, right? Everywhere, okay? And here it will be in this direction, right? And due to I1, magnetic field will also be in this direction, but it will be very small, right? It will be very small. So from this, we can see at every point, magnetic field is always perpendicular. So A option is correct, right? For the B option, saying depends on X, Y only through the radial distance. Okay, so look, we can't find the magnetic field definitely, but look, if we make just a radial plane like this, a circular loop like this, due to symmetry, we can say the magnetic field at any point will be according to this distance, radial distance. Due to symmetry, we can say, right? Because look, the magnetic field is not proportional to radially here, so it will not be here, right? So it will not be here. So at every point, magnetic field should be different. But look, as it is symmetric, magnetic field in the circular should be equal, right? So by symmetry, we can say it will only uh, depends only through the radial distance. So B option is correct, right? Now let's move on to C option. So we have BXY is non-zero at all the points for R less than R. So in this region we are talking about. So let's first find the magnetic field at O. So magnetic field at O is due to 1. So it will be B1, and magnetic field will be due to B2. So let's first find B1. So it will be out of the plane, right? So it will be mu naught I1 divided by 2R dot, right? And B2 will be mu naught I2 upon 2 into 2R. It will be the z direction, right? And if you try to find this, we can see B2 is greater than B1 because I2 is greater than 2I1, right? I2 is greater than 2I1. In the question it is given. So look, what will happen? What will happen is that at center, magnetic field is more in the due to this red wire. So at the center, magnetic field will be into the plane, right? So B naught will be into the plane, right? Now look, as you move towards this wire, at just point here, at just here, right? At just here, the magnetic field due to 1 will shoot to infinity, right? And at here, magnetic field due to second wire will shoot to infinity. But look what happens as you move like here, as you move like here. What will happen? The magnetic field due to I1 increases more compared to B2. Of course, magnetic field due to this second wire will also increase, but the increase in one will is more. So as I can say, increase in B1 is more than increase in B2. Okay, are you getting me? So this B1 is magnetic field due to first in the smaller circle, and B2 is due to bigger circle, right? So increase in B1 is more than increase in B2 as you move radially outward. So at some point, as B2 is more at center, at some point there will be a situation where B1 is exactly equal to B2, right? And at that point, magnetic field will be zero. So C option is incorrect. Okay, so C option is incorrect. Now for D, magnetic field at our point normally outward from xy plane for all the point between the normally outward from xy plane for all the points between two loops. Okay, so what is saying? So this point is wrong. Look, in this region, magnetic field is inside the plane, right? And it is saying normally outward. So this point is absolutely wrong. So A and B are. So this question is quite interesting. We'll consider it as a moderate. Concept is pretty nice. Okay. So this is important, which I have written here, right? So let's move on to our next question. 11th question here. So this is our 11th question. We have two infinite long straight wire lie in xy plane along the lines this. Okay. Located at a point. So we have, let me make the plane, right? The figure is like this. So we have a wire, we have another wire. Okay. So in this it has I1 current, and in this it has, so the locate which is located at x equals to plus r. So this has I1, this will have I2. This is x equals to minus, right? This is x-axis, and this is y-axis. Okay, perfect. A circular loop of radius r is suspended at its center and in the plane parallel to xy plane. Okay, so let me make the diagram again. Let's make the diagram we take this as x, this as y, and this as z, right? Okay, now we have wire like this. Okay, so this has current I2 and this has current I. This is x equals to r and this is x equals to minus r. And we have a loop like this which is parallel to xy plane at a distance 0, 0, root 3. So we have a loop like this. This point is at root 3. Okay, the radius of this loop is r. The loop carries a current, constant current I in clockwise as seen from above. So if you see it from above, you will see the current is in clockwise direction. So it's like this. If you see it from here, okay, right? The current in the wire is taken uh, to be positive if it is in positive. Okay, perfect. So it's not given. So wire is like this. So we have wire like this. Okay, these are infinite wires. Okay, let me make this is our wire and this is our second. Okay, and this we have our like okay. If I1 is equals to I2, then B cannot be equal to 0 at origin. If I1 is equals to I2. So if you take them in the same direction, then at center magnetic field due to these wires. So due to this it will be in the plus Z, and due to this it will be minus Z. But due to loop there will be magnetic field at the center, right? So even if like current in both is same, right? Magnetic field cannot be zero because the loop will be due to loop there will be magnetic field at this point. So A is correct. Next. If I1 is greater than 0 and I2 is less than 0, so the current in this is like this, and in this it will be in opposite direction. Okay, now what happens is the magnetic field can be 0, can be equal to 0 at origin. So due to this, magnetic field will be in this direction. So let's say this is third. Okay, so this is third loop. So this is 1, 2, and this is third current carrying. So B1 is like this, B2 will be like this, and due to this, right, due to this, so if you are looking it from above, the magnetic field it is in clockwise, so it is in clockwise, so magnetic field will be like this. Magnetic field must be like this, right? So here magnetic field will be B3 downwards, right? So if you increase the current, maybe B3 can counter B1 and B2, so B option is also correct, right? Let's move on third option. If I1 is less than 0, so I1 is like this, right? And I2 is like this. So we have just changed the direction of the current, right? B can be equal to 0. So look, due to I1, B1 will be like this, and due to I2, B2 will be like this. So it can never be 0. So C option will be wrong. Okay. Now if I1 and I2 are equal, then Z component of magnetic field at the center of the loop is this. If I1 and I2 are equal. So if I1 and I2 are equal, then at this point, right, due to one magnetic field will be uh, so let me make a diagram like this. So this will be the perpendicular distance, the magnetic field will be like this. Okay, so if I'm considering I1 like this, right, and I2 is also equal, so I'm considering the direction to be same. Okay, so due to I1, right, magnetic field should be like this, and due to I2, magnetic field should be like this, B2. Okay, and due to this loop it will be in the downward direction. right? So this will be B3. So we have at this point B1 is like this, B2 is like this, and we have B3 like this, and B3 will be mu naught I by 2R, right? Look, for B1, let's say this is our angle theta, okay? So if I consider this as a theta, so this will be theta, right? So let's just take this as theta. So if this is theta, then this will be theta, right? And if this is theta, then this must be theta. So this must be theta, okay? So we can see B2 cos theta and B1 cos theta. So in Z direction, there will be B1 cos theta in upper direction, right? B2 cos theta in downward direction, and we have B3. So these two will get cancelled. So only B3 will be there. So D option is also correct. In Z direction, the magnetic field at the center of the loop will be only due to the loop itself. Okay, so D is correct. So this is quite an interesting question. Easy, but a bit complicated. Not that it's easy, right? So let's move on to our 12th question. So we have a steady current I. We have a steady current I flows in along an infinite long hollow cylinder conductor of radius r. Okay, so we have a loop like this, and this is a hollow loop, right? Of radius r, and current flowing is I, right? Sorry. Uh, this cylinder is coaxially placed inside an infinite solenoid of radius 2r. So we have a solenoid like this, and they are coaxially placed. Okay, let me make a diagram like this, right? And the radius of this is 2. It, n is given turns per unit of length, right? Carries current I. So it also carries a current I. Consider a P point at a distance r from the common axis. Choose the correct statement. Okay. So in the region 0 to r, so in between there is only magnetic, so the magnetic field due to cylinder at these points, right? So for r greater than 0, less than r, magnetic field due to cylinder will be 0 if you make imperial loop, but magnetic field due to solenoid will be mu naught ni, right? So the magnetic field is non-zero, so A option is correct, right? So A option is correct. Next, in the region R, like in this region, right? So in this region we are talking about. So first, so second, the magnetic field is along the common axis. Let's check. So due to this, if we have to make a ampere loop like this to make the to solve the magnetic field due to cylinder. So it will be in this direction. So if I want to find it this, magnetic field will be inside the plane, right? So it will be here, but so this is due to cylinder, right? But due to loop, it will be in this direction, right? So let me just remove this. So this is due to cylinder, and this will be due to solenoid. Okay. So due to solenoid, it will be along the axis, but due to cylinder, it will be inside. Okay. Along the common axis, that is wrong. In the region R to 2R, the magnetic field is tangential to the circle or radius R. Again, it is wrong. It is tangential as well as perpendicular to the loop. Okay, so again this is wrong. In the region R to R, the magnetic field is non-zero. Of course it is non-zero, it will be due to cylinder. So A and D will be the option. Okay, so quite easy question it is. You just have to, you know, uh, make the 3D diagram and understand the situation. Okay, so if you can visualize this 3D uh, diagrams, then the concept will be very easy, right? Okay, let's move on to our, this was 12 and this will be our 13th question. So we have a long wire, current carrying wire. So I1 says that I1 is flowing out of the plane. So here we have a current carrying wire, infinite, right? A steady current I2 is flowing in this loop, right? The net force is zero on the loop. Let's check if net force is zero or not. So due to this, magnetic field will be like this, okay, along this. And here it will be, let's say this is B1, let's say this is B, and here let's say it will be B2, right? So here it will be again B. This B will be variable because it will change as you move along B to C, right? So force on AB is zero because I2 cross B is zero. Are you getting me? I2 cross B, because current is in this direction and B1 is in this direction. So the sine theta will be zero, right? So I'll just write theta is zero. And this is same for force on CD. It is also zero because again theta is zero. Now for this, look on BC, the force will be, if you use Fleming's left hand rule, so the force will be out of the plane. So here force will be like this, and here force will be into the plane. Okay, of course it will be variable, but it will be constant. It will be same for BC and AD, right? It will be variable. The net force you can definitely find, but it will be same for BC and CD. So A option is correct. What about torque? So look, on BC the force is towards you, but on AD force is inside the plane. So there will be a torque about OO dash. So B is wrong. Okay. Let's check C. As seen from O, the loop will rotate in the clockwise. So look, on BC, the force is in towards us, right? And for AD, it is towards. So if you stand here, you will see BC is moving like this. So if you see it from here, you will see BC will move like this and it will move like this. So you will see this will be moving in clockwise direction. So C is correct. As you know, the roof, so it is of course wrong. So A and C is the correct option, right? Let's move on to our 14th question. So it's incomplete. Let me add the other parts. Okay, so it's not there, but I will give you the options to you. Okay, so let's uh, check this question. We have current carrying I flows along the length of an infinite long straight thin walled pipe, right? So it's slender like we have current I thin walled pipe, right? So I mean this is a hollow cylinder. Magnetic is quite simple, right? The magnetic field at all the point inside the pipe is same but not zero. Actually, it will be zero. So this option is wrong. The magnetic field at any point inside the pipe is zero. So this is correct. So C option was magnetic field is zero only on the axis of. So it's saying B is zero only on axis of pipe. So of course this is wrong. At every point it will be zero if you make Amperian loop. The magnetic field is a different at different point inside the point. So B, it's saying B is not zero at uh, inside the So it will be different. So this is also wrong. So only B option is correct, right? Let's move on to our next question. So this was 14. Now this will be 15th, right? Okay. So we have a cylindrical cavity. So this is a cylinder like this, okay? Like this. Infinite cylinder of diameter 2a as shown. Both the cylinder and the cavity are infinitely long. Okay, perfect. The uniform J flows along with this at a point. So it is P. Yes, at P point we have to find the magnetic field. So it's this. Okay, let's first find the magnetic field due to cylinder. So it will be B into 2 pi A, right? We have to make an Amperian loop like this. We'll make an Amperian loop like this, okay? So it will be mu naught. The current will be total. So it will be J into pi A square, right? So we'll get pi A will get cancelled and we'll get magnetic field will be mu naught JA by 2. Okay. Now due to this, so we will make a Amperian loop. This time it should be like this, right? Considering this as a center. So 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 this is due to cylinder and due to cavity, right? So due to cavity, it will be mu naught into the loop. So look, this is total. So this will be a by 2 and this is a. So it will be 3a by 2. So it will be 2 pi 3a by 2, right? The circumference of the Amperian loop and the current it enclosed. So it is enclosed what? J into the area will be pi a by 2 whole square. Okay, quite easy. So we cancel these things, so it will be mu naught j pi a square by 4 and this will be 2, so this will be 3 pi a, so it will be 3 pi a. So pi again will get cancelled, a will get cancelled, so we'll get b will be equals to mu naught j a by 12, right? And we have to subtract this because this is a cavity. So b at p will be b due to cylinder minus b due to cavity. So it will be mu naught J A by 2 minus mu naught J A by 12. So 12 will be LCM. So it will be 6 minus 1. So it will be 5 mu naught J A, right? So N will be 5, right? Let's move on to our 16th question. So a steady current I flows through a loop PQR having a shape of right angle triangle. Okay. So Q, let's say this is Q, this is R, and this is P, right? So this is 5x, this will be 3x, right? PQ is 3x and this is 4x. Now magnetic field at P. So we have to find the magnetic field at here. So due to PQ and PR, it will be 0. Only the magnetic field will be due to QR. So let's make a perpendicular distance like this. And this distance, let's say if this is theta, so this is 4x, so this distance will be 4x sine theta, right? Okay. Now magnetic field at P, it will be simply the current is like this, right? So magnetic field will be mu naught I by 4 pi into perpendicular distance. This will be 4x sine theta into sine theta 1. So sine theta 1 will be this, right? So this is theta, this is 90 minus theta, and this will be theta. So it will be sine theta plus sine 90 minus theta, right? So let's just put all those values. So it will be mu naught I upon 4 pi 4x, and let's just divide sine theta. So it will be 1 plus cos theta upon sine theta. So we're having mu naught I upon 16 pi x and this will be 1 plus cot theta. So cot theta will be base upon perpendicular. So base is 4, perpendicular is 3. It will be 4 by 3. So we will get 7 mu naught I upon 48 pi x, right? So simply k will be 7. Okay, quite easy question. Let's move on to our last question of this session. So this is quite interesting question. Okay, in this question it is saying the all the wires is having same current, right? So let's solve. So look, if you use right hand thumb rule, magnetic. So let's say this is first, this is second. Okay, so at this point current is same. So magnetic field due to one will be inside and due to two will be outside, and they will be same, right? So it will be opposite. So Q is correct, and there is no magnetic field. Net magnetic field is zero, right? Okay, let's check the B option. So for the B option, again, the magnetic field, okay, and the force. So force will be if the magnetic field here will be this. So if current is in same direction, they attract. Okay, so you can also find with the Fleming's right hand rule. So force will be on this wire will be in this direction, and on this it will be in this direction. So they will attract. So S option is wrong. Now for this, uh, again the magnetic field at P. So this, let's say this is 1, this is 2. Magnetic field at P is in this direction due to 1, and due to 2 it will be in this direction also, right? So magnetic field for both of them at P point will be in the same direction. So P option is correct, right? Q is wrong, R is wrong. And how will we check if they attract or repel? So let's just this behaves like a magnetic dipole, right? So we'll make a magnet like this. So if current is in this direction, then this must be north, this must be south, and again we'll make like this. So this must be north, this will be south. So what will happen? They will attract each other. So S option is wrong. Okay, right? You just make a magnet. The situation will be very easy. At point P, so at point P, look, this P point is very close to this section of wire. Okay, so we'll just check due to this. So due to this section, the current is in this direction, and due to this section, current is again in this direction, right? So for both of them, current in the same direction, then again what will happen? A magnetic field will cancel each other out, right? And this is asymmetric, so magnetic field at P must be 0. So again, Q and R will be the correct option. And for S, okay, let's check. So again, we'll make a magnet like this. So if this is in anti-clockwise direction, right? So north will be like this and south will be behind, right? And for this, the south will be like this, right? So if I make like this, they will be like this. So north, south, and this magnet will be south and north. So of course they will attract each other, and they will, yes, if you put two magnets like this, they will attract each other. So again, S option is wrong. Next, P is situated at the common center at this. So magnetic field due to this wire, the small loop will be, uh, so let's say this is first, this is second. So due to one, it will be out of the plane, right? So it will be like this. And due to two, it will be inside the plane, right? And we know magnetic field is mu naught I upon 2a, right? So look, this is R1, this is R1 minus mu naught I upon 2 R2. And this is, we say, R2. Of course, R1 is more, So magnetic field due to one will be more. So it will not be zero, but it will be opposite, right? So Q is correct. It will not be zero. The wires will repel each other. Let's check this. So look, we have a wire like this, and this is our second wire. Now current in this wire is like this, and current in this wire is like this, right? So let's just check this this part of the wire, right? So in this, the current is in opposite direction, so they will attract each other. Similarly, this will attract each other. Similarly, this will attract each other, right? So force on each section will be like this. Oh, okay, so it's in opposite direction, right? Sorry. So it will be repelling each other, right? So it will repel each other because current is in opposite direction. Now you will say, sir, what about this section and this section? Look, this section will be applying force, but it will be small. So I'm just considering this section because they are the closest to each other. So the force will be maximized due to them. And this situation is whole symmetrical, right? So it will be like this. Let me make the diagram properly. So we have like this, and this is like this, right? Look what happens at this section of wire. All the other section will be applying force, but the force due to this section will be maximum. So we'll say net force will be like this. So they will be repelling. So it's like this. Again, on this section, all the other section will be applying force, but this section will be applying the maximum force and which will be repelling it, right? So at that, the net force will, so they will be actually repelling each other. So it will be S, right? So S will be correct. Okay. So this question is again quite interesting, quite conceptual, but it was not that tough. Okay. So let's finish today's video. Thank you